all the segments where you have more than one reactor, so your mixed water reactors in series or phosphorus series, that will be covered. Has anybody attempted these problems? Okay, one. That's pretty good. Okay, so because all the solutions are given, I've picked one out which I thought encompassed everything. So I'm going to go through today question 2 in 2011 for last year's bucket. So nobody's looked at this apart from one. Have you done this one? Okay, so the solutions are given, but I'm going to basically point out what the things that you guys need to bear in mind while attempting this. And I'll go through with you as if we're doing this. Okay, so the question, I've actually put on, but I don't know if you guys can see. Can you guys see this? Or is it too small? You can't see? Can't see? Okay. I will do that. Okay, so I'll put this on. I'll just switch to. Okay, so with this, I'll just go through this. So in this question, what it's asking is, okay, you've given this first order elementary reaction. Okay, so the key point here is first order and elementary. Okay? And you'll ask, okay, if the reactor is performed in a batch reactor, so another key word is a batch reactor. And it's in aqueous phase. What does it mean when it's in aqueous phase? There's no volume change, so the expansion factor here is 0. So that's very important to know. And then basically I want to show that when T, this expression, how do you get this expression? How's that to right? Okay, and then we know that that equation there is made up of the conversion factor, the conversion of A, equilibrium conversion, and K1, and then T. So when we look at this, it's basically that's a performance equation. So you need to do the integration. So I'll do this on this. So we start off with, the equation. I'll put this up here, just so we can refer to it for those that can see. So always sort of watch what that equation, the rate equation is. That is R, so the K1 and K2. Can you see that? Yeah? Okay, so we know that it's elemental. So what I like to do is write down the keywords down. So as you do these solutions, when you're working it out, you don't have to reread the whole sort of paragraph again. So write down the key points. So elementary, we know it's first order, and we know it's aqueous phase. So EA is equal to 0. So this is for 2A. Okay? So, and what other information do we know or assume? Okay, one thing to assume is that initial CR0 is 0 to start off with. Okay, so first we'll write down the rate equation. RA, so that is equal to CA dt, which is equal to CA0 XA dt, and that is equal to You're going to complete it for me? Yep, so K1 CA minus K2 CR. And now what we need to do in order to solve that is to convert the A and the CR to XA only. So we need to rewrite that expression. So we know CA is equal to CA naught minus CA naught XA. So this is what we start off with initially. And this is we minus the amount that's been converted to R. But because we've got the CR term, so this here is what is being going backwards to the initial, so the reverse reaction. So CR, so we know CR naught, so initial, and we know that that's 0. Okay? And because here the A is being consumed, so with CR it's being generated. So it's got opposite sign, and we know that it is a 1-to-1 ratio. So basically the amount of, so if it's 1-to-1 ratio, if we have this amount of A being consumed, we'll have the same amount of this amount being generated for R. Okay? So that will be plus CA naught XA. So now we have your two, we have re-expressed CA and CR to only one variable, which is XA, conversion of A. So if we sub these one into this equation there, so we'll rewrite that is equal to, I'll omit this part. So this would be K1 CA naught minus CA naught XA minus K2. So this is just CA naught XA. So we can simplify this. Let's get all XA together, collect them together, because that's the variable that we have. So if I expand the bracket, there, and then we collect these together. Minus the plus, be careful with the sign. Okay, so now we can simplify that further. So we can take this one out the front, so that's 1 minus bracket in here, the same thing, 1, and that will be plus. The same thing, these two takes out, so it will be K2 over K1. Okay? It's simpler. So then, what we need to do is work out what to relate K2 and K to K1. So, in order to, what we need to do here is use this equation here. So, basically, we know that at equilibrium, so look over here, it says, oh, I don't quite. So we know at equilibrium, Ra is equal to 0. So at equilibrium, there's no reaction going on. So it's reached at equilibrium conversion. So we can, for this expression here, we can get that to equate to 0. So it's easier to use this than this one because now we've got K1 and K2 here. So if we go back to here again, if we equate that to equal to 0, so K1 is equal to 0, then this is very important. So that's now a constant, so we know the equilibrium conversion. And so now we can get K2 over K1 is equal to K1 CA naught minus CA naught A over XA. And we can simplify that. So CA naught. So I should have simplified this back up here. Is equal to CA naught A. This will cancel out. So K2, K1 is equal to 1. So I'm dropping E. So make sure you don't drop that E to let you know that that's an equilibrium conversion. So now we have an expression for what relates K2 and K1 together. Are you guys following so far? Yeah? Okay, so what we now need to do is, we know the rate equation here, alright, and it's all in terms of XA only, because we know that's a constant, and that's a constant as well. We can relate K2 and K1 using this expression here. And, okay. So if you look at this equation here, what we ask is to get T, okay, in terms of these parameters. So you will be given, we know that it's a batch reactor, and in the test paper you're given the expression to find out what the time is for a batch reactor. Okay, so that is, I'll just write it here, is equal to So we need to relate time. So this is given in your test paper, is equal to naught and it's given in that form, okay? And for batch reactor, that volume there is a volume of fluid that goes in that batch reactor. And with that volume, you know that because in this case it's the liquid, it's an aqueous phase, EA is equal to 0. Normally, you need to put 2B. You'll notice that B is equal to B naught plus XA, to take into account expansion factor if it was in a gas phase. But because it's a liquid, this is equal to 0. Okay? So that means B is simply B naught. So we can rewrite this as simply CA naught over B naught, because that's a constant. That's the initial, the amount of material going in. Naught divided by R. So with the volume, if it's, okay, so we'll bring that over here, and we know this is simply CA naught. Okay, so that's the key expression you need to get to. And because we already said what our, where is it? What the RA is up here. So if we put that in, T equals CA naught So you're going to be careful when you're doing the integration to make sure that you be careful when you're copying out your expression. Because if you make a mistake earlier by copying out the rate equation wrong, that means if you go through that long interval, everything is just not going to work out. You can spend ages trying to work out to get you back to that expression, but if you make a mistake here, you won't be able to get it. So make sure you copy out exactly what